Okay. Okay. So I want to describe quite recent work with Chang-Sik in KAIST on the Walker satellite constellation. It's one of these low orbit constellations. So as you have seen, we have quite we have quite a lot of projects and action. You have seen Sanjoy and Ashutosh lectures on this topic, and I want to so they were looking at very essential topics, and here what I want to do is to give a picture of the overall constellation and the Shannon rate and estimation of global properties of these constellations, right? Okay, so that's the aim. So I will describe what these guys are, and I will describe communication networks based on these constellations. And novelty is interplay between geometry and dynamics of these objects. You have seen already in the two talks, I mean, things which were not purely the geometry, but also the dynamics. I mean, handover is a dynamical aspect, and in a sense, of course, the Doppler shift as well, right? Okay, and the main new thing is that we start understanding this interplay a bit more precisely, right? Okay, so I didn't take it for granted that you would know what the Walker classification is. I will describe it. There is the star, the delta, and I will not give the full blow description. I will just look at the case of circular orbits, one altitude. Sanjoy discussed the multi-altitude case, which is very important for most constellations. And there are lots of variants that I will not describe. And so these pictures sort of describe what these guys are. The Walker on the left, delta, which is the basis of Starlink and Galileo, has all its orbital planes with the same inclination, and the ascending points, which are the places on the equator where the trajectory of the orbit goes from south to north, equally arranged on the equator. Whereas the star, I will not describe it as almost polar orbits, and you get only on a half equator ascending points, and you will get the descending points on the other half of the equator, right? Of course, Earth rotates, as some believe, and so a given user will sometimes see satellites on the equator moving up, and other times moving down, right? For the star, but I will not describe the star. Okay, that's the delta, and I want to study this one. Because why? Because this is the, as we shall see, do you see this or not? Yeah. See a little bit? Okay, so this is the this is Starlink constellation, and actually it has a mix of a delta and some part also are a star. To cover the polar regions, and there are holes and a little bit of randomness, right? But what people had in mind is this, and this is what people want to do, and all the projects you heard. I think Ashutosh and perhaps Sanjoy alluded to the work with Constellation technology, which is this ESA startup. And they have about 1,000 satellite constellation project in the millimeter wave of 5G. That is their project. And this is the delta. Okay, and so this is and I will describe that in a bit more detail. Okay, so what's the point, right? For communication, it's these constellations with low orbit are used. Of course, they are why are they developed? Because of short RPTs, right? So think of the altitude of Starlink is between 300 and 500 kilometers. So the speed of light, you see, get things of the order of the millisecond for just one trip. And so you can get things if you want to do lots of interesting, important things in communication, sensing, and things like that. Of course, very differently from the RTTs that you would have for geo constellations or the geo systems, geostationary systems. Okay, there are lots of things for this which are these things are used for, but for broadband, it's a new coverage solution which is universal, at least in the latitudes which are below the max latitude for the orbits. Without interruption, if there are sufficiently many satellites on the orbits, broadband, low latency, and resilient. I will not describe that too much, right? There are lots, and there are lots of completely new questions. So base stations, basically, if you think of cellular networks, first are moving, which is something completely different. Users might move, and there are lots of completely new things. It was alluded to the visibility cap, which comes from the geometry. The new assessments of interference with this spherical geometry, beam management, handover, multi-hop routing was alluded to, lots of things, right? And there was one of the questions coming from, I think, Marco about edge computing, right? Okay, so here is the first question for you. Think of, describe the thing. So you have the orbits, which are arranged periodically. You have the satellites, which are periodically arranged on each orbit, right? And first question that we asked ourselves, I mean, seen from a given point on Earth, do you see something periodic? The ephemerides. So ephemerides are very important. You have your phones, you will have your antennas, you need special antennas to talk to these phones. And which beamform to the satellites, follow it, and hand over when needed, right? And so the ephemerides of the satellite are very important, of the constellation is very important. So what is your guess? Periodic, non-periodic? Periodic. Okay, thanks. So Patrick knows the answer, and it will come soon, right? Okay, so let me start with the things. Indeed, what are the orbits? What are the Voronoi things which are important for handover? What is coverage? What is spectral efficiency? What is Shannon rate? These are the other questions. Okay, so there is a long history now, which starts about year 2020. The first to ask these questions is Nilufa Okati in Finland. In her thesis, she didn't look at the Walker at all. She looked at the so-called binomial point process on the sphere. You take points which are uniformly distributed in the sphere for a given number, independently and uniformly, and you use stochastic geometry, which is computable in that case, to look at all these questions. But there are no orbital planes. There is no dynamics. It's a static thing. Okay, and of course, it's very different. If you just eyeball the thing, the Walker, which is the aim of all these low orbit constellations for reasons I explained, is very different in terms of clustering from the binomial case, right? Okay, so let me repeat. The Walker I concentrate on, and that's a new thing, as its orbital plane, which field inclination regularly spaced over longitudes with random phase. So the first, as the Earth rotates, there is a first phase of the, say, the first orbit seen from Greenwich, which is the offset, right, of this periodic thing. And satellites on each orbit are equally spaced, and again with random phase, right? Okay, so let's not be the number of orbits. As I said, I repeat what I said, you would have, and in the mental pictures that I want to, which will be very important in a second, these N0 ascending points are distributed regularly, namely periodically on the equator, with initial phase for the first seen at a given time from Greenwich, which is uniform on 0 to pi over N0, right? Okay. And same thing for the satellite, and there's number of satellites on each orbit. It's a regular case. Can think of later things a bit later we discuss. Phases of the NS satellites, again, on each orbit are periodic on 0 to pi with an initial phase that I will take in this model the same for all orbits and it will be omega, which is uniform on 0 to pi over ns, right? And so you get a point process of at time t equal to 0, which is the set of deltas on the sphere of radius of Earth plus altitude of the constellation. This is your model. This is the point process at time 0. But then there is dynamics. Okay, you can compute lots of things. If you take this as a snapshot in the first place, then, for instance, you can compute which out of a closed form, I can explain here. DL, think of a typical user at distance at latitude U, right? And think of the distance from the typical user at latitude LU to its nearest satellite. Okay, and you can prove if there is no satellite, you can put a mass at infinity. And what you can give is a closed form expression, integral expression, for the probability of that this distance is more than constant d, right? So this is the TDF of the distance at which, under this distribution that I just described, I will explain its importance a bit later, at which you see the nearest satellite, which will give you the best signal, right? The one you will connect to, right? And here already you see something quite interesting, is that there is a cap. If there are sufficiently many satellites, for instance, here N0 is 30 orbits with 50 satellites per orbit, then there is a DC, a critical value of V, such, which is about 770 kilometers, above which you never find, you will always find a satellite below this quantity, right? So it's very different from all the Ocati and early things, so which gives a very important service guarantee for because it's signal, right? A close satellite is signal. So you can, in the same vein, get the total interference and the SINR in terms of closed form expressions, which are in terms of integrals. So let me skip that and move to the dynamics, which is really the answer to the question I asked, right? So that's the second part. I will need a few more minutes. Sorry. Okay. So you have this initial phase, and now you add time. You add time, right? So you have this thing with this offsets. And what happens? Earth rotates, and the satellite, they rotate at a constant speed on their orbits, right? And so there is a basic dynamical system, which I call R, which lives on the torus, which gives the angle of the initial first angle of the first trajectory orbit on the equator, and the offset of the first satellite on each of the orbits. And these are the rotations on the torus, which were studied in dynamical system. And you can, out of that, including now the rotation of Earth and the speed of rotation of satellite, see how the point process, which you at the time t on the sphere, evolves on the sphere. And there is a closed form expression. And you get out of that the key result, which comes here. So this dynamical system, the one on the torus, has an invariant measure, which is exactly the one I described in the model. This is the only invariant measure for this rotation on the torus. And when you push forward this thing, you get the stationary distribution of the satellite, namely the law of the ephemeris of the constellation. And there is a classical result for in the dynamical system for the rotation of the torus. And the first theorem that we get here is the answer to to my question and the disproof of Nina's conjecture. If the ratio of the speed of Earth's rotation, which is given by the gods, and the speed of rotation of satellites, which is given by Newton's plus the altitude, if this ratio is rational, then Nina is right. But if this ratio is irrational, then this is wrong. and the ephemerides are chaotic and admit as an invariant measure the measures that I used in my calculations. Okay, that's a very short summary. And out of that, if it is ergodic, long-term averages seen from a typical user location at a given latitude will converge in long term, as the Birkhoff theorem shows, to the expectation computed that I computed earlier. Okay, so let me stop here. I want just to stress more globally that this work with the Koreans is part of Uber-Korean interaction with South Korea. Chang-Si just started at KAIST. There's a lot of work currently, as you have seen, the frequency of handovers, that's the work which Joy described. There is this very important activity on the distribution of Doppler shift, which is very, we are working with also South Korean colleagues on the RIS enhancements of NTN and routing and things like that. Okay, so let me give a few references and show a way to compute ephemerides in South Korea in the 17th century.